We'll continue our discussion on lecture 3, harmonic function, conjugate harmonic function and Milne-Thomson method. Before we start the Milne-Thomson method, I will say something. If the function f of z is analytic in the complex plane, then u and v both are harmonic function or both are analytic function, but the converse part is not true. That is, if u is harmonic function or v is harmonic function separately, then from this we cannot be say as necessarily f of z is analytic. But by the Milne-Thomson method, we have seen that f of z is analytic function and u and v are the conjugate harmonic function. That means u and v both are satisfied the Cauchy-Riemann equation. If one of these, say u, is given, then determine f of z directly without finding v is due to Milne-Thomson method. So basically Milne-Thomson method is a very interesting and very useful method for finding the analytic function or finding the function f of z. So if there is a function u is given but v is not here or v is not given, then from this we will directly find the function f of z without applying or without finding v. Similarly, when v is given, so from this we will directly find f of z without finding u. So that is the proof of the theorem basically. So let z is equal to x plus iy. This is this is the complex point, variable point, and therefore z bar is equal to x minus iy. So z bar is equal to this is the conjugate of z, and z bar is equal to x minus iy. So from this we'll get from this two equation we'll get x and y. So if we cancel y from these two, we'll get x, and the value of x is equal to 1 by 2 into z plus z bar, and the value of y is equal to 1 by 2 into z minus z bar. Okay, so these are the value of x and y with respect to z and z bar. Okay, now we are looking for find the function f of z, and f of z is equal to u of x comma y plus I into v of x comma y, and if we put x is equal to this and y is equal to this, so we will get the value with respect to z and z bar. So f of z is equal to u of x z plus z bar by 2 comma z minus z bar by 2i, as well I into v of z plus z bar by 2 comma z minus z bar by 2i. So now we put z is equal to z bar, that means y is equal to 0 and x is equal to z, so that f of z is equal to u of z comma 0 plus I into v of z comma 0. Okay, now we are going to find the first derivative of f of z. So f of z is equal to derivative of f of z is equal to f dash z, and this is equals to del u del x plus I into del v del x. So applying the CR equation, and it will change and it will give del u del x minus I into del u del v. CR equation of complex function. So now we will choose del u del x is equal to phi 1 of x comma y, and del u del y is equal to phi 2 of x comma y. So del u del x and del u del y are both are the continuous function, and both are function of x comma y. So that's why I will choose del u del x is equal to phi 1 and del u del y is equal to phi 2. Okay, now we put phi 1 x comma y and phi 2 x comma y in the place of del u del x and del u del y. Then the first differentiation f dash z will be changed, and it will be phi 1 x comma y minus I into phi 2 x comma y. Okay, so from this, if we put x is equal to z and y is equal to 0, this is actually the proof of the Milne Thomson method. So f dash z is equal to phi 1 z comma 0 minus I into phi 2 z comma 0, where x is equal to z and y is equal to 0. Same. So now integrating this, we get f of z is equal to integration of phi 1 z comma 0 minus I into phi 2 z comma 0 dz plus c, where c is an arbitrary constant. That is, from Milne Thomson method we can find f of z without finding v. That is, f of z is equal to phi 1 z comma 0 minus I into phi 2 z comma 0 dz plus c. This is the function of f of z. Okay, where phi 1 and phi 2 are the given functions. So phi 1 is equal to del u del x and phi 2 is equal to del u del y. So phi 1 and phi 2 are the two partial differentiation with respect to x of the function u. Okay, where c is a arbitrary constant. We are going to find f of z without finding u. Okay, so here is the expression of the function f of z. This is actually similar as the first one. So if we put del v del x, del v del y is equal to psi 1 of x comma y, and del v del x is equal to psi 2 of x comma y. So we'll get the function f of z, and f of z is equal to integration of psi 1 z comma 0 minus I into psi 2 z comma 0 into dz plus c, where c is an arbitrary constant, you know. Okay, next we are going to talk about some related problems on Milne Thomson method. So the first problem is actually the proof that u, so u is given, u is equal to x to the power 3 minus 3xy plus 3x square minus plus 3x square minus 3y square plus 1 is a harmonic function. Next we are going to find the analytic function u plus iv, that is f of z without finding the function v. So u is equal to xq minus 3xy plus 3x square minus 3y square plus 1. If del 2 del x square plus del 2 del y square is equal to 0, then we will say this function is a harmonic function. So here u is equal to this. So from this we are going to find the first order partial differentiation with respect to x, and then we are going to find the second order differentiation with respect to x. So the first order differentiation with respect to x, and it will be 3x square minus 3y plus 6x, where y is constant, so 3y square plus 1 is 0 with respect to x. And del 2u del x square is equal to, so derivative of 3x square is equal to 6x, and 6x is equal to 6. So the second order differentiation with respect to x is equal to 6x plus 6. And similarly we are going to find the derivative for the function u with respect to y. So first of all we are going to find the del u del x. So del u del x is equal to minus 6xy minus 6y, where x is a constant term. Okay, so this is actually the partial differentiation. So from this we are going to find the second order differentiation, and it will be minus 6x minus 6. So therefore the second order differentiation with respect to y and second order differentiation with respect to x, or 2x del 2u del x square plus del 2 del y square, and it will be okay, after considering the term 6x minus 6 we'll get this is actually 0. So this is actually the Laplace equation, you know. So the second order and first order partial differentiation are exist as well. The function u satisfy the Laplace equation. So from this we will say this function, that is u, is a harmonic function. So next we are going to find the analytic function without finding v. So if we apply the Milne-Thomson method, we can find the analytic function without finding the conjugate of u actually. So here, so if the function is analytic and satisfy the Cauchy-Riemann equation, then from this we have to find the analytic function f of z without finding v. And similar thing will happen when v is analytic and satisfy the Cauchy-Riemann equation. Then from this we have to find f of z without finding u. Okay, this is the Cauchy-Riemann Milne-Thomson method. So here u is given and u is also the harmonic function. So that means u is an analytic function, and u is satisfied the Cauchy-Riemann equation. So what is the Milne-Thomson method when u is given? So this is the expression of Milne-Thomson method. So f of z is f dash z is equal to phi 1 z comma 0 minus I into phi 2 z comma 0. So I have already mentioned in the previous slide, this is the expression of f dash z, or that is f of z is equal to integration of phi 1 z comma 0 minus I into phi 2 z comma 0. So here del u del x is equal to phi 1 of x comma y, and del u del y is equal to phi 2 of x comma y. Okay. So phi 1 of x comma y is basically partial differentiation first order with respect to x, and it will be 3x square minus 3y square plus 6x, and phi 2 of x comma y, and this is actually the partial differentiation of u with respect to y, and it will give minus 6xy minus 6y. Okay, so at x is equal to z and y is equal to 0, phi 1 of a z comma 0 is equals to 3z squared. Okay, y is 0, the second term is 0, and the third term is 6z. That is phi 1 of z comma 0 is equal to 3z square plus 6z. And similarly, when we put x is equal to z and y is equal to 0 in the second expression, we'll get phi 2, the value of phi 2 at x is equal to z and y is equal to 0, we'll get minus 6 into z into 0, that is the first term is 0 as well, the second term is 0. So f dash z is equal to and the value of f dash z and is equals to 3z square plus 6z minus I into 0. Okay, so now integrating we get integrating on both sides, we get f of z is equal to, so integration of 3z square is equal to z cube, integration of 6z is equal to 3z square plus c, where c is an arbitrary constant. Okay, next we are going to talk about the second problem. Next we are going for okay, we are looking for the second problem. If a function, analytic function f of z, find the analytic function. We will go for the second problem of Milne-Thomson method. Find the analytic function f of z is equal to u plus iv, of which the imaginary part b is equal to e to the power x into sine y. So here the function that is the imaginary part b is given. So from this we are looking for find the analytic function f of z without finding u. So that means we are going to we are that means we'll apply the Milne Thomson method for finding the analytic functions. So here b is given, and so u is not given in this problem. So b is equal to e to the power x into sine y. So if b is given, then what is the Milne Thomson method? The Milne Thomson method is actually f dash z is equal to psi 1 z comma 0 plus I into psi 2 z comma 0. This is the Milne Thomson method, and I have already discussed in previous slide. So where psi 1 z comma 0 is equal to del v del y, and psi 2 of z comma 0 is equal to del v del x. Okay, so here x is equal to z and y is equal to 0. This is the this is actually the So this is the formula of Milne Thomson method. So here the partial differentiation for the function b with respect to x. This is when y is constant. So del v del x is equal to, so derivative with respect to x of for the function e to the power x is e to the power x. Sin y is constant, and it will give phi 2 of x comma y, say. So phi 2 of x comma y is the function. Okay, and it will be e to the power x into sin y. And similarly, del v del y, this is the partial differentiation with respect to y, and it will give e to the power x into derivative of sin y. So derivative of sin y is cos y, and we'll say it is psi 1 of x comma y. Okay, so now putting x is equal to z and y is equal to 0 in the first and second expression, and we'll get e to the power z, first one. So e to the power, okay, in the first expression we'll get 0, that is phi 2 of z comma 0, it will be 0. So sin 0 is equal to 0. And in the second expression, if we put x is equal to z and y is equal to 0, we will get e to the power z into 1, that is e to the power z. Okay, now integrating on both sides, and from we have to find, after integration, f of z is equal to, so integration of e to the power z is equal to e to the power z plus c, where c is an integrating or arbitrary constant. Okay, so next I will take one more example of Milne Thomson method. So here is the example. If so u minus v is equal to x minus y into x square plus 4xy plus y square, and f of z is equal to, you know, f of z is equal to q of x comma y plus I into b of x comma y is analytic function of z is equal to x plus I y. Then find f of z in terms of z. So here u and v, that means u minus v is given, though both functions are not individually given. Okay, so from this we are looking for either we can find u or we can find v. Then we will apply the Milne Thomson method, and after applying the Milne Thomson method, we will get the function, analytic function f of z in terms of z. Okay, so let's start with our solution. So here f of z is equal to, you know, u of x comma y plus I into b of x comma y is an analytic function. So now, and it satisfies the Cauchy-Riemann equation, you know. So del u del x is equal to del v del y, and del u del y is equal to minus del v del x. So this is the condition of Cauchy-Riemann equations. So if the function is analytic, then it will be satisfied. So that means the Cauchy-Riemann equation is satisfied. So, and also u minus b is given. So u minus b is equal to x minus y into x square plus 4xy plus y square. Okay, so now differentiate this equation. We'll get del u del x minus del v del x, and after differentiation we'll get this x square plus 4xy plus y square, and derivative of x minus y is equal to 1. So similarly, when x4 minus y is constant, then differentiation of this function is 2x plus 4y. Okay, so now applying, now applying the Cauchy-Riemann equation, you know del v del x is equal to minus del u del y. So del u del x plus del u del y is equal to this, and similarly we can find the differentiation with respect to y, and from this we'll get this one, del u del y minus del v del x is equal to this. So again we apply the Cauchy-Riemann equation, we'll get del u del y minus del u del x is equal to this. Okay, so from equation 2 and this equation, say this equation number 3, so from these two equations we'll get the value of del u del x and del u del y. So after cancelling the term del u del x from equation 2 and equation 3, we'll get del u del x and del u del y. So here the del u del x is equal to 6xy, and this is equals to say phi 1 of x comma y, and del u del y is equal to phi 2 of x comma y. Same. So now applying the Milne-Thomson method, we'll have f dash z is equal to phi 1 of z comma 0 minus I2 I into phi 2 of z comma 0. So here phi 1 of z comma 0, that means if we put x is equal to z and y is equal to 0, we'll get the value of 0. Similarly, for the second case, if we put x is equal to z and y is equal to 0, we'll get 3z square. So f dash z is equal to 0 minus I into 3z square. Okay, so now integrating on both sides, we'll get f of z is equal to minus 3z to the power 3 by 3. This is actually, there is some mistake here. So it will be actually 3z to the power 3 by 3, that is after cancelling the term 3, we'll get minus I into z to the power 3 plus c, where c is an arbitrary constant. And this is the last problem on lecture 3. Determine the analytic function f of z where b is given. So here b is equal to x to the power 4 minus 6x square y square plus y to the power 4. So from this we are going to find the partial differentiation with respect to x and respect to y. So the partial differentiation with respect to x is equal to this 4x cube minus 12xy square, and it will be phi of x comma y, same. And similarly, if we differentiate it with respect to y, and it will give minus 12x square y minus plus 4y to the power 3, and say it will be phi 1 of x comma y. Okay. Now applying the Milne-Thomson method, it will give f dash z is equal to phi 1 z comma 0 plus I into phi 2 z comma 0. Okay, now if we put z comma 0 in the second expression, we'll get the first term is 0 as well as the second term is 0. And similarly, we'll put if we put z is equal to x is equal to z and y is equal to 0 in the first expression, we'll get 4z cube, and the second term is 0 actually. So f dash z, and it will give 0 plus I into 4 z to the power 3, that means 4iz cube. So now integrating on both sides, it will give f of z is equal to iz to the power 4 plus c. So derivative or integration of z2 is equal to z to the power 4 by 4, and 4 is cancelled from numerator and denominator, it will give this, but c is an arbitrary constant. I will stop here. Thank you.